I would now like to present you with a grand overview of the key properties of the determinant. I will give enough detail now for you to get a general idea of what each property is saying. And of course, I'll give much greater detail in later videos when we discuss each of the elements individually. Also in this video, I will show you how we'll navigate from the algebraic definition of the determinant to each of its properties. As I mentioned before, how one chooses to navigate this tapestry, how one chooses what's the definition and what's the consequence, is a matter of personal preference. As a matter of fact, I think you should be able to start at various places here and be able to get to every other place. Interestingly, until now, we've been using this governing property as our starting point. That is, we've been constructing algebraic expressions built up from the entries of the matrix that equals 0 when the matrix is singular and not 0 otherwise. And that's how we came up with all of those very nice expressions for small matrices. Well, we're now switching from that old strategy to a new strategy where we'll start with this algebraic definition and then we'll proceed to prove each of the properties pretty much according to the arrows that I've drawn. And just to help you orient yourself to this board, let me again show you the sequence in which it was drawn. All right, let's begin. We will start with this algebraic definition. There is no question that this definition looks daunting. However, all the properties that follow from this definition are so elegant that I'm sure that you will come to think of this definition as inevitable as opposed to daunting. This definition states that the determinant equals the sum of n factorial terms. Each of the terms is a product of n entries from the matrix, chosen in such a way that there is exactly one entry from each row and one entry from each column. And the rows are chosen in order. The columns are chosen according to some permutation denoted by epsilon. And that's why they're exactly n factorial terms, because they're n factorial possible permutations. And there is a term in the determinant corresponding to each possible permutation. And the sign that comes with the term, plus or minus, depends on the parity of that permutation. And so in order to understand this definition, you will have to understand permutations and their parity. The first property that we will show is that the determinant of A transpose equals the determinant of A. And this will prove to be a very important property. It will enable us to go back and forth between talking about the columns and the rows of the matrix. Because after all, the columns of A are the rows of A transpose. And the columns of A transpose are the rows of A. So if we're able to make some statement about how the determinant depends on the columns of the matrix, then we can immediately make the same statement about its dependence on the rows of the matrix. So that's the significance of this first property. The second property that we will show is that the determinant of a triangular matrix, whether it's upper triangular or lower triangular, and of course those two kinds of matrices are related by the transpose, is the product of the diagonal entries. Let's take an upper triangular matrix, for example. The entries below the diagonal are 0, of course, and the entries above the diagonal may not be 0, but they don't matter. The only terms that matter for the determinant are the ones that are right on the diagonal, and the determinant equals their product. And so out of the n factorial terms, a single term, the product of the diagonal entries survives. And it always comes with a plus sign. And so this gives us our first category of matrices of arbitrary size for which we can easily calculate the determinant. And it might seem like a very narrow category of matrices. But of course, later properties will tell us that the calculation of any determinant can be reduced to that of a triangular matrix. And that's why it's so important to establish this simple property early on. Then we'll move on to this group of properties united by the figure bracket. And they're united by that bracket for a very good reason that I will explain in just a moment. The first of these properties is that the determinant of the identity matrix of any size equals 1. Of course, this property follows immediately from the triangle property, but it does deserve to be stated on its own. Next comes the signature property of the determinant. It states that when one switches two columns in a matrix, the determinant changes sign. For example, it would go from 5 for the original matrix to -5 for the matrix with the columns switched. This property is known as antisymmetric or alternating because the sign of the determinant keeps changing for every switch of two columns. It may not seem like much, but this property of the determinant is the key to its greatness. One of the immediate consequences of this property is this one. If two columns in the matrix are equal, then the determinant of that matrix is 0. Why? Well, simply because if we were to switch those two columns, then on the one hand, the determinant will be unchanged because the matrix itself remained unchanged. After all, those two columns were the same. On the other hand, because of the alternating property, the determinant will change sign. And the only number that equals minus itself is 0. And of course, everything that we just said about the columns of the matrix can also be said of the rows of the matrix thanks to this property. So, when one switches to rows in a matrix, the determinant once again changes sign. And if two rows of a matrix are equal, then the determinant is necessarily 0. The next two properties come together and are called linearity, or linearity with respect to individual columns, because they tell us how the determinant responds when a particular column is a linear combination of two or more vectors. And as you're about to see, the determinant responds very linearly. I sometimes like to call this property simply distributive, because it is very reminiscent of the common distributive law. But I don't think anybody else calls it that, so let's stick with the word linear. And on the board, I have linearity represented by two separate properties. The first property tells us what happens when a particular column is multiplied by a number. And what happens is very simple. The whole determinant gets multiplied by that number. For example, if you have a matrix whose determinant is 7, and you pick a column and you multiply just that column by 10 and leave all the other columns unchanged, now you have a new matrix whose determinant is 70. It's that simple. It's linearity at its purest. The next property is nearly as simple. It tells us what happens when a particular column is a sum of two vectors. And what you end up with is the sum of two determinants, where in the first one you have the first vector for that column, and in the second one you have the second vector for that column, and all the other columns are unchanged. That's linearity. And I really think that the words that I just used and the equations that you see on the board make linearity seem more complicated than it really is. You should see it as a very basic and simple property. And if you want to see it as simply as possible, you should think of the following analogy. You should think of the determinant, as far as linearity is concerned, or any other function described by the word linear, as the total amount of money that you pay when you go grocery shopping. And if you go and you buy 10 apples, then the price you have to pay for 10 apples is 10 times the price for a single apple. How simple is that? And if you buy an apple and a banana, that's what the second property will describe, you have to pay the price of an apple and the price of a banana. That's what linearity is trying to say, and that's how simple it is. And I'm sure that you can also see how to combine these two properties into a single one that will tell us what happens when you have a linear combination of fruit. For example, if you buy 10 apples, alpha A, and 5 bananas, beta B, then the total price that you'll have to pay for alpha A plus beta B is 10 times the price of a single apple plus 5 times the price of a single banana. That's linearity, and that's the simple thing that these two properties are trying to say. Now, just a couple of notes. Number one, it is very important that these properties apply to individual columns. They tell us what happens when a single column is affected. So if more than one column is multiplied by a number, you would have to apply this property several times, one for each column. And if two or more columns are thought of as a sum of two vectors, you would have to apply this property twice, and then once again to each of the two expressions, and then once again perhaps to each of the four expressions. So it is beginning to very much look like the distributive law, or maybe the act of foiling. So very important, individual columns only. That's why the determinant is sometimes called polylinear or n-linear, because it's not linear in the overall sense that if you multiply a matrix by 10, the determinant is multiplied by 10. That's not what happens. Or if you add two matrices, you have to add the individual determinants. That's not what happens either. So the determinant in that sense is not linear. It is only linear with respect to each individual column, or with respect to every column, and that's why individually. And that's why it's called polylinear or n-linear. That's number one. Number two, thanks to the transpose property, whatever we just said about columns also applies to rows. So if you have a matrix and one of the rows is multiplied by a number, then the whole determinant is multiplied by that number. Or if you have a matrix and a particular row is a sum of two vectors, then it ends up being a sum of two determinants, where in the first one, the first vector stands for that row, and in the second one, the second vector stands for that row. All right, and finally, from this property, we immediately get this property, that if a matrix has a zero column or row, then its determinant is 0. Why is that? Well, very simple. Let's imagine multiplying this column by 10. On the one hand, thanks to this property, the determinant got multiplied by 10. On the other hand, because it is a zero column, the matrix remained completely unchanged, and therefore its determinant remained unchanged. And so we're looking for a number that's 10 times itself. That's the determinant of that matrix. It's 10 times itself. And the only number that has that property is 0. So we got this property right here from this one essentially for free. And I think you're beginning to see how we're inexorably marching towards this property, that if a matrix is singular, or half of this property, going in this direction, then the determinant is 0. Because these two properties that we've encountered so far are characteristic of singular matrices. And in both cases, we had to conclude that the determinant is 0. And we did so very simply. So we're not here yet, but we're definitely going in that direction. What will essentially get us here is this property, which tells us what happens when we add a multiple of one column to another and leave all the other columns unchanged. Well, I'll tell you what happens in just a moment. But first, I'd like to note that you should mentally group this property with this one, which tells us what happens when we switch two columns, and this one, which tells us what happens when we multiply a column by a number. And why do these three properties belong together? Well, it is because if we were to restate them in terms of rows, they would give us the determinant response to each of the Gaussian elimination operations. And once again, why are we able to restate them in terms of rows? Well, it's thanks to the transpose property. Well, now let's get back to this property, let's say in terms of columns, and say what happens when we add a multiple of one column to another. Well, nothing happens. The determinant remains unchanged. This is the only way this equation fit on the board. And we can prove right here now why the determinant remains unchanged. Very simple proof. Look at this matrix. It has a sum of two vectors for a column. So it can be analyzed by this property. And according to this property, half of linearity, this determinant will split into two determinants. In the first one, B will be in its rightful place all by itself. So we'll have the unchanged matrix A and its determinant. In the other determinant, once we factor out alpha according to this property, the other half of linearity, we'll have a matrix with two identical columns. And by this property right here, that determinant will be 0. So this determinant splits into two. One of them is A, and the other one is 0. So this determinant equals the determinant of A. So we now know the determinant response to each of the Gaussian elimination operations. Let's state them in terms of rows. When we switch to rows, the determinant changes sign. When we multiply a row by a number, the determinant is multiplied by that number. And when we add a multiple of one row to another, the most common of all Gaussian elimination operations, I think, the determinant remains unchanged. And so now, two wonderful things happen. Number one, we get a perfectly efficient way for calculating determinants, in contrast to the algebraic definition, which has n factorial terms and is in no way efficient. In fact, it's so inefficient that it's hardly ever used. But the strategy that we have now, thanks to knowing the determinant response to each of the Gaussian elimination operations, is as follows. When we have to calculate the determinant of a matrix, simply perform Gaussian elimination on it and keep track of the changes that those operations imply for the determinant. Change sign, multiply by a number, leave it unchanged. And then, when you end up with an upper triangular matrix as a result of Gaussian elimination, simply multiply the diagonal entries together, and that's the determinant. Super simple. And that's the way that the determinant is usually calculated in practice. All right, so that's number one. That's the first wonderful thing that happens. The second wonderful thing that happens, really a watershed event for the whole thing, is that we now have this property right here. And we can go both ways with it. Let's go this way first. If a matrix is singular, then in the course of Gaussian elimination, you will get a row or a set of rows that are all zeros, which means that in the upper triangular form, we will have a 0 on the diagonal. And therefore, the determinant, being the product of the diagonal entries, is 0. So we have just proven that if a matrix is singular, the determinant is 0. Let's go in the opposite direction. If the determinant is 0, then by this strategy, it means that post-Gaussian elimination, there will be a row there will be a 0 on the diagonal. That's the only way that a product of several numbers can be 0. That's if one of them is 0. And because one of the pivots, elements on the diagonal, is 0, we'll have to conclude that the matrix is singular. And therefore, if the determinant is 0, then the matrix is singular. So we have proven the equivalence between being singular or having linearly dependent columns and having determinant 0, which is the end towards which we've been working all along. So how easy was that? And now we're left with two of the most magnificent properties of the determinant. The first one is geometric, and it is at the very heart of the determinant's prominence in applied mathematics. The second one is algebraic, and it is crucial for the algebra of determinants. And of course, the two are intimately related. The first one states that in 2 dimensions, the determinant of a 2 by 2 matrix equals the area of the parallelogram built upon the vectors that correspond to the columns of the matrix. In 3 dimensions, the determinant of a 3 by 3 matrix is the volume of the corresponding 3-dimensional parallelepiped. That's amazing, isn't it? If you're learning this fact for the very first time, you're amazed, aren't you? I mean, you've calculated areas and volumes before, and almost always it involved lengths and angles and other geometric elements like that. Never determinants. Well, maybe in multivariable calculus, you've seen glimpses of this when you were working with Jacobians. But still, it's amazing just how clean this statement is. There are really no words to describe how amazing this property is. And now let me clarify it in several very important ways. First of all, things like parallelograms and parallelepipeds and areas and volumes are very much geometric. On the other hand, things like columns of a matrix and determinants are algebraic. How do you reconcile the two? In the spirit of treating all objects on their own terms, it is my responsibility to explain what I'm talking about. How do we go from geometric vectors to columns in a matrix? Well, we do it in the standard way. We choose an orthogonal basis consisting of orthogonal vectors of unit length. And we decompose each one of these vectors with respect to this basis. And we organize the resulting coefficients as columns of a matrix. And we can do the same thing in 3 dimensions with respect to a basis with 3 vectors, consisting of orthogonal vectors of unit length. All right, this is the standard way of going from geometric vectors to vectors in R2 or R3. And it's precisely what I've been discouraging you from doing until now. And I've been discouraging you from doing it because it hasn't been necessary, we haven't needed it. And it's very important to appreciate that this hasn't been necessary. Well, it's necessary now, and so we're talking about it. And we'll talk about it even more when we're studying component spaces later on. Number 2, as you know, determinants can be positive and negative, but areas and volumes are always positive. So how do you reconcile that? Well, we have to start talking about signed areas. This is areas that can be positive and negative. And you've already seen this kind of thing in calculus, where the area below the horizontal axis was negative, and the area above the horizontal axis was positive. Well, here, positive and negative will be defined differently. It has to be defined differently. Here's how it's going to be defined. In 2 dimensions, this parallelogram is said to have positive area if you have to label vectors as first and second, just like the corresponding columns in the matrix, first and second. And if the shortest path from the first to the second is counterclockwise, the area is positive. And if it is clockwise, then the area is negative. And we will find that if we label this vector first and this vector second, that the corresponding determinant will be positive, consistent with the area. And if we label this one as first and this one as second, then the area will be negative and the corresponding determinant will be negative. In 3 dimensions, you have to do something a little bit more sophisticated. You have to use the right-hand rule. In 3 dimensions, you label vectors as first, second, and third, just like columns in the matrix. First, second, and third. And then you sweep these 4 fingers of your right hand from first vector to second. And if the thumb on the same side of that plane as the third vector in the mix, then the parallelepiped is said to have a positive volume. And if it's on the other side of the plane from your thumb, then the volume is negative. And we will once again find that that's consistent with the sign of the corresponding determinant. What about in 4 dimensions? Well, let's be very clear here. There is no such thing as areas and volumes in 4 dimensions. Geometry does not extend to 4 dimensions, so the question is moot. However, this is where determinants come in a very crucial way. In 4 and higher dimensions, the logic is really turned on its head. There, we will define volume as the determinant of the corresponding matrix. So do you see what happens here? We're poetically inspired by what we see in 2 and 3 dimensions and metaphorically extended to higher dimensions. This sort of thing happens in applied mathematics all the time, and linear algebra is always at the center of these kinds of extensions. All right, finally, how might we prove this property? At first, you might think that the demonstration has to rely on sophisticated geometric arguments. Well, actually, the proof will be much more algebraic and much simpler. You will recall that I mentioned earlier that this definition implies these 4 properties. But on the other hand, these 4 properties imply this definition. In other words, if you have a function of matrices that satisfies these 4 properties, it has to be the determinant. It can't be any other function. So what we will show is that area, signed area as we defined it, actually satisfies these 4 properties. And if it satisfies these 4 properties, it must be the determinant. Actually, let's sketch the proof right now because it will be very much uncomplicated. If we look at the first property, the determinant of the identity matrix, well, what geometric vectors does the identity matrix correspond to? Well, of course, because it's 1, 0, and 0, 1, it's the vectors of the basis itself. And what's the area of the corresponding parallelogram? Well, it's the unit square, so its area is 1. And of course, this vector is first, and this one is second, so it's plus 1. So the determinant is 1, and the area is 1, or I should point here rather. Okay, the first property matches. What about the second property? Well, what happens if we switch 2 vectors? This used to be first and this used to be second, and the area was whatever it was, a positive number. And now we're calling this first and this second. Well, now it's the same area, but with a minus sign because now we're traveling in the clockwise direction. And so once again, the area changes sign, just like the determinant does. So the second property matches as well. And finally, the third property is very clear. If one of these vectors, just one, is multiplied by a number, let's say 2, then it's very clear that the corresponding parallelogram will also stretch by a factor of 2. So its area will increase by a factor of 2. And so the third property holds. And finally, the last property, which will actually require a little bit of work. To prove the last property, we have to imagine that one of these vectors is a sum of a set of another 2 vectors. And what we need to show is that this parallelogram, the area of this parallelogram, equals the sum of the areas of 2 parallelograms, where the first one is built on this vector and one of the other 2. And the second one is built on this vector and the other one of the other 2 vectors. So that will not be too complicated, but it will require a little bit of geometric work. And once we show that, we'll conclude that the area, signed area, satisfies these 4 properties, and it must therefore equal the determinant. So let's recap. The determinant in 2 dimensions equals the signed area of this parallelogram. In 3 dimensions, it equals the signed volume of the corresponding parallelepiped. In 4 dimensions, there's no such thing as areas and volumes, so the determinant is used to define the 4 and higher dimensional volume. And finally, the proof of this property is much simpler and much more elegant than you would think. And finally, the surprising property that the determinant of a product of two matrices is the product of the individual determinants. Surely you can tell how an identity like this is absolutely crucial to the algebra of determinants. But why did I call it surprising? Well, it's because it's simply hard to believe that such a simple identity could result from such a complicated definition. Just imagine using this definition to prove this identity for 3x3 matrices. It would probably take you over an hour just to write out the left-hand side. Go ahead and try it. Actually, don't try it. Maybe attempt it, but make sure to quit after 5 minutes. Yet this identity is true for matrices of arbitrary size. And while the direct algebraic proof of this identity, based on this definition, is quite cumbersome, unless you invent a superior notational system, the geometric, yes, geometric intuition behind this identity is quite simple. Soon, we will learn to think of matrices as transformations of space. In essence, a 2x2 matrix whose columns correspond to these two vectors in the sense that we just discussed can be thought of as a deformation of the plane that deforms the elements of the basis into these two vectors. And then the determinant tells us the amount by which areas get stretched. With this interpretation in mind, what we have on the left-hand side of this identity is two transformations, one stacked on top of the other. And then the determinant on the left-hand side tells us the amount by which areas are stretched as a result of this combined linear transformation, this sequence of linear transformations, one after the other. And if one of the linear transformations stretches areas by 5, and the other transformation stretches areas by 3, then the combined transformation, the sequence one after the other, will surely stretch areas by a factor of 15. 5 times 3. 5 times 3. 5, the amount by which one of the transformations stretches areas, times 3, the amount by which the other transformation stretches areas. And that's the simple geometric intuition behind this wonderful identity. And that's the intimate connection between these two of the most magnificent properties of the determinant. All right, next we'll discuss each of the elements on the board individually.